Imagine standing at the edge of a cosmic shoreline, where the familiar laws of physics begin to bend, and whisper secrets we're only just beginning to understand. Tonight, we're journeying into one of the universe's most profound mysteries, the slow, patient dance of black holes as they give themselves back to the cosmos, one quantum whisper at a time. These gravitational giants, born from the collapse of massive stars, hold within their event horizons a story that challenges everything we thought we knew about permanence, time, and the very nature of existence itself. Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starry night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe because tonight, we're exploring one of Stephen Hawking's most beautiful discoveries, the revelation that even the darkest objects in our universe slowly return their borrowed energy to the quantum sea from which all things emerge. We'll drift through the mathematics of curved spacetime, swim in the gentle currents of Hawking radiation, and discover how these cosmic lighthouses of gravity teach us that nothing in our universe is truly eternal everything, even the most massive black holes, eventually returns to the quantum foam from which it came. Let's begin this journey together, settling into the comfortable embrace of cosmic time, where billions of years pass like gentle breaths, and even the most permanent-seeming objects in our universe slowly fade into the soft glow of thermal radiation. Our story begins not with the death of stars, but with the birth of ideas, gentle thoughts that emerged in the quiet minds of scientists over a century ago. Picture Albert Einstein in 1915, sitting in his study as autumn light filtered through tall windows, wrestling with equations that would fundamentally reshape our understanding of space and time. His general theory of relativity was like discovering that the universe itself was made of fabric, a fabric that could be stretched, twisted, and curved by the presence of matter and energy. Within months of Einstein publishing his revolutionary equations, a German physicist named Karl Schwarzschild made a discovery that would echo through decades of cosmic exploration. Schwarzschild was serving as a soldier on the Russian front during World War I when he found an exact solution to Einstein's field equations, a mathematical description of how space and time curve around a perfectly spherical, non-rotating mass. Tragically, Schwarzschild died of an autoimmune disease just months after his discovery, never knowing that his solution would become the foundation for understanding some of the most exotic objects in our universe. The Schwarzschild solution painted a picture both beautiful and strange. It described how spacetime curves more and more dramatically as you approach a massive object, like the gentle slopes of a hill becoming steeper and steeper until they form a cliff. But unlike any cliff on Earth, this was a cliff in the very fabric of reality, a point where the curvature becomes so extreme that space and time themselves seem to fold back on themselves. For decades, this remained purely theoretical, a mathematical curiosity that most physicists assumed could never exist in nature. The equations suggested that if enough matter were compressed into a small enough space, it would create a region where the escape velocity, the speed needed to break free from the gravitational pull, would exceed the speed of light itself. Since nothing can travel faster than light, this would create a boundary from which nothing, not even light, could escape. This boundary came to be known as the event horizon, and the region within it became known as a black hole, a name coined much later by physicist John Wheeler in 1967, though the concept had been lurking in the mathematics for over half a century. The event horizon isn't a physical surface like the skin of a balloon, but rather an invisible boundary in spacetime itself, a point of no return that exists wherever the curvature of space becomes so extreme that all paths, even those of light itself, curve back toward the center. What makes this boundary so fascinating is that it's not the same distance from the center for all observers. Space and time become so intertwined near a black hole that measurements of distance and duration depend entirely on where you're standing and how fast you're moving. An astronaut falling toward a black hole would experience time normally from their own perspective. But to a distant observer watching through a telescope, the falling astronaut would appear to slow down more and more as they approached the event horizon, their image becoming redder and dimmer, until it faded from view entirely. This is the first hint of the deep strangeness that surrounds black holes. They exist not just as objects in space, but as warps in the very nature of space and time themselves. They are, in a sense, places where our usual notions of here and there, now and then, begin to lose their familiar meaning. But perhaps the most profound realization about black holes wouldn't come until the 1970s, when a young physicist named Stephen Hawking began to wonder what would happen if you combined Einstein's curved spacetime with the strange, probabilistic world of quantum mechanics. This marriage of general relativity and quantum theory would reveal that black holes are not the perfect prisons they were once thought to be, but rather cosmic engines slowly converting their own mass into the gentlest possible form of energy thermal radiation, so soft and subtle that it would take longer than the current age of the universe to detect it from even the smallest black holes. To understand how black holes can evaporate, we must first journey into the quantum realm, that strange territory where particles pop in and out of existence, like fireflies blinking in a summer meadow. Quantum mechanics tells us that empty space isn't really empty at all, but filled with a constant, gentle activity that we call quantum fluctuations. These fluctuations are like the universe's quiet breathing pairs of particles and antiparticles spontaneously appearing, and then almost immediately annihilating each other, returning their borrowed energy to the quantum vacuum. Picture this happening everywhere, all the time in the space between atoms, in the vast reaches between stars, even in the emptiest regions of intergalactic space. Under normal circumstances, these virtual particle pairs live for such incredibly brief moments that they have no observable effect on the larger world around us. They appear, dance together for a quantum instant, and disappear, leaving the universe unchanged. But Stephen Hawking realized that near the event horizon of a black hole, something extraordinary happens to these quantum fluctuations. The extreme curvature of spacetime near the black hole can sometimes separate these particle pairs before they have a chance to find each other and annihilate. When this happens, one member of the pair might fall past the event horizon into the black hole, while the other escapes to infinity, becoming a real particle that carries energy away from the black hole. This process is so subtle, so gentle, that it took one of the most brilliant minds in physics to recognize it. Hawking published his discovery in 1974, showing that black holes must emit a steady stream of thermal radiation with a perfect blackbody spectrum, the same kind of gentle glow that comes from any warm object, whether it's a piece of heated metal or a star's surface. But here's where the story becomes truly beautiful and strange. The temperature of a black hole's radiation is inversely related to its mass. The more massive the black hole, the cooler its radiation. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree, above absolute zero, far colder than the cosmic microwave background that bathes all of space. This means that stellar mass black holes are actually absorbing more energy from the universe around them than they're emitting, causing them to grow rather than shrink. Only black holes much smaller than our Sun would be hot enough to evaporate faster than they grow. A black hole with the mass of a mountain would glow with the temperature of room air. One with the mass of an asteroid would shine as bright as the Sun. And a microscopic black hole, with the mass of just a few atoms, would burn as hot as a nuclear explosion, evaporating in a brilliant flash of gamma rays. This inverse relationship between mass and temperature means that as a black hole evaporates, it gets smaller and hotter, causing it to evaporate faster and faster in an accelerating process. But for the black holes that actually exist in our universe, those born from the collapse of massive stars or the mergers of smaller black holes, this process is so incredibly slow that it defies comprehension. Consider a black hole with the mass of our Sun. It would take approximately 1067 years to evaporate completely. That's a 1 followed by 67 zeros, a number so large that it makes the current age of the universe, a mere 13.8 billion years, seem like a single heartbeat in cosmic time. The supermassive black holes that lurk at the centers of galaxies, with masses millions or billions of times that of our Sun, would take even longer time scales, so vast that they stretch the very meaning of eternity. During most of this unimaginably long evaporation process, the black hole would emit mostly photons, particles of light so low in energy that they would be virtually undetectable against the background radiation of space. These photons would carry away the black hole's mass energy bit by bit, following Einstein's famous equation E equals mc2, which tells us that mass and energy are two faces of the same cosmic coin. But Hawking's discovery revealed something even more profound than just another way for objects to radiate energy. It showed that black holes have temperature and entropy thermodynamic properties that connect them to the fundamental laws that govern how energy flows through the universe. This connection between gravity, quantum mechanics, and thermodynamics opened up entirely new ways of thinking about the nature of information, the arrow of time, and the ultimate fate of our universe. One of the most beautiful aspects of Hawking's discovery is how it revealed that black holes follow the same fundamental laws of thermodynamics that govern everything from steam engines to living cells. These laws, first developed to understand how heat flows and work gets done, turn out to be among the most universal principles in all of physics. They apply equally to a cup of cooling coffee and to the most extreme gravitational objects in the universe. The first law of thermodynamics is essentially a statement about the conservation of energy. Energy can be neither created nor destroyed, only transformed from one form to another. For black holes, this means that as they emit Hawking radiation and lose mass, that mass energy is being converted into the thermal energy carried away by the escaping particles. The black hole isn't violating conservation of energy. It's simply transforming its gravitational mass into radiative energy, following the same principle that allows our Sun to shine, by converting a tiny bit of its mass into light. The second law of thermodynamics tells us that the entropy of an isolated system can never decrease. Disorder tends to increase. Hot things cool down, and organized structures tend to become more random over time. This law seemed to create a puzzle when applied to black holes, because if you dropped something with entropy, say, a hot cup of coffee or an encyclopedia full of information, into a black hole, it seemed like that entropy would simply disappear from the universe, violating the second law. But in 1973, Jacob Bekenstein, then a graduate student, made a remarkable proposal. He suggested that black holes themselves have entropy, and that this entropy is proportional to the area of their event horizon, not their volume. This was a radical idea because in ordinary thermodynamics, entropy usually depends on volume. The more space available for particles to move around in, the more ways they can be arranged, and thus the higher the entropy. For black holes, however, the entropy is written on their surface, encoded in the very geometry of the event horizon itself. The larger the black hole, the greater its surface area, and the higher its entropy. This means that when you drop that cup of coffee into a black hole, the black hole's entropy increases by at least as much as the entropy that disappeared with the coffee, preserving the second law of thermodynamics. When Hawking discovered that black holes radiate, this thermodynamic picture became complete. The temperature of the radiation is exactly what you would expect from an object with the entropy that Bekenstein had calculated. Black holes behave like perfect thermal objects. They have temperature, entropy, and they radiate energy according to the same laws that govern the gentle glow of warm coals in a fireplace. But there's a crucial difference between a black hole and an ordinary thermal object, like a piece of hot metal. When a hot piece of metal cools down by radiating energy, it loses temperature and approaches thermal equilibrium with its surroundings. A black hole does the opposite as it radiates energy and loses mass. It actually gets hotter and radiates faster. This means that black holes are thermodynamically unstable. They run away from equilibrium rather than toward it. This runaway behavior is what drives the evaporation process. Once a black hole starts losing mass faster than it gains mass from its surroundings, it enters a phase of accelerating evaporation. The smaller it gets, the hotter it becomes, and the faster it evaporates, until in its final moments it releases all of its remaining mass energy in a brilliant burst of high-energy particles and radiation. During the vast majority of its evaporation lifetime, however, this process is almost unimaginably gentle. A solar mass black hole would spend most of its 1067-year lifetime emitting photons with energies comparable to radio waves, the softest form of electromagnetic radiation. These photons would be so low in energy that billions of them would need to be absorbed to warm a single atom by even a tiny fraction of a degree. The radiation process is also completely random and thermal, like the gentle glow from any warm object. The black hole doesn't remember what fell into it in any detectable way. The radiation that emerges has no obvious connection to the specific matter and energy that originally formed the black hole or fell into it over its lifetime. This creates what physicists call the information paradox, one of the deepest unsolved problems in theoretical physics. If information is truly fundamental and cannot be destroyed, where does the information about the matter that fell into a black hole go when the black hole finally evaporates away? To truly understand how black holes can create particles from empty space, we need to dive deeper into the strange relationship between geometry and quantum mechanics. Imagine spacetime as a vast, flexible membrane, something like an infinite sheet of rubber that can be stretched, twisted, and curved by the presence of mass and energy. Near a black hole, this membrane is curved so severely that it creates conditions unlike anywhere else in the universe. In flat, empty spacetime, the kind you might find in the vast regions between galaxies, quantum field theory tells us that the vacuum state, the state with the lowest possible energy, is well-defined and stable. Virtual particle pairs constantly appear and disappear, but they do so in perfect balance, creating no net effect on the larger world around them. The mathematics of quantum fields in flat spacetime has been worked out with extraordinary precision, and it matches experimental observations to better than 1 part in a billion. But curved spacetime changes everything. When spacetime is curved by gravity, the very definition of what we mean by empty space, or vacuum, becomes ambiguous. What looks like empty space to one observer might appear to be filled with particles to another observer who is accelerating or moving through a gravitational field. This isn't just a matter of perspective. It's a fundamental feature of how quantum fields behave in curved spacetime. Near a black hole's event horizon, the curvature of spacetime creates what physicists call a gravitational redshift. Time itself runs slower in stronger gravitational fields, and this time dilation affects the quantum fields that permeate all of space. From the perspective of a distant observer, the quantum fluctuations near the event horizon appear to be redshifted, stretched out in time, and reduced in frequency. This stretching of the quantum fluctuations is what allows some of the virtual particle pairs to become real. Normally, virtual particles exist for such brief moments that they must annihilate before they can affect the outside world. But near the event horizon, the extreme curvature of spacetime can stretch these quantum fluctuations over longer periods of time, giving them enough breathing room to become real particles that can escape to infinity. The process is remarkably similar to what happens during the expansion of the universe itself. In the very early universe, the rapid expansion of space stretched quantum fluctuations beyond their virtual limits, turning them into real particles and ultimately creating the seeds that would grow into galaxies and stars. Near a black hole, the extreme curvature plays a similar role, providing the energy needed to promote virtual particles into real ones. But there's a crucial conservation law at work here. Energy cannot be created from nothing. When a virtual particle near the event horizon becomes real and escapes to infinity, carrying positive energy away from the black hole, its partner must carry negative energy into the black hole to balance the books. From a distant observer's perspective, the escaping particle appears to have been created from the vacuum, while the negative energy partner disappears beyond the event horizon, reducing the black hole's mass by exactly the amount of energy carried away by the escaping particle. This negative energy might seem strange, but it's a natural consequence of quantum field theory in curved spacetime. In regions of strong gravitational fields, it's possible for quantum fields to have negative energy density, at least temporarily, and in limited amounts. This negative energy is what allows the black hole to shrink even as it creates particles from seemingly empty space. The rate at which this process occurs depends sensitively on the curvature of spacetime near the event horizon, which in turn depends on the black hole's mass. Smaller black holes have higher curvature and create particles more rapidly, while larger black holes have gentler curvature and create particles more slowly. This is why the temperature of Hawking radiation is inversely related to the black hole's mass. Smaller black holes are hotter because their more extreme spacetime curvature creates higher energy particles at a faster rate. The mathematics describing this process is both beautiful and complex, involving the subtle interplay between general relativity and quantum field theory. It requires sophisticated techniques from both classical geometry and quantum physics, including methods for calculating how quantum fields behave in curved backgrounds and how observers in different reference frames perceive the same physical processes. The information paradox. When quantum mechanics meets general relativity, one of the most profound puzzles arising from Hawking's discovery concerns the fate of information when black holes evaporate. This puzzle, known as the black hole information paradox, sits at the heart of our understanding of how the universe works at its most fundamental level, and it has driven decades of research into the deep connections between gravity, quantum mechanics, and the nature of information itself. The puzzle begins with a basic principle of quantum mechanics. Information is conserved. If you know the exact quantum state of a system at one time, the laws of quantum mechanics allow you to calculate its exact state at any future time. Information about the past is encoded in the present state of the system, and this information can, in principle, be recovered through sufficiently detailed measurements. This principle works beautifully for ordinary physical processes. When you burn a book, the information contained in its pages isn't destroyed. It's scrambled and distributed among the smoke, ash, and heat that result from the burning. With a perfect knowledge of quantum mechanics and unlimited computational power, you could, in principle, track every molecule and reconstruct the original book from the products of combustion. The information is still there. It's just become incredibly difficult to access. But Hawking radiation seems to violate this principle. The radiation that emerges from a black hole appears to be perfectly thermal, completely random, with no information content beyond its temperature and total energy. If this radiation truly contains no information about what fell into the black hole, then the evaporation process would destroy information, violating one of the most fundamental principles of quantum mechanics. Consider what happens when you drop an encyclopedia into a black hole. The encyclopedia contains enormous amounts of information. Every letter, every page, every detail of its physical construction. According to classical general relativity, this information crosses the event horizon and becomes inaccessible to the outside world. But it still exists inside the black hole. However, when the black hole eventually evaporates via Hawking radiation, this information seems to disappear entirely. The radiation carries away the mass energy that originally came from the encyclopedia, but none of the specific information that made the encyclopedia unique. This creates a fundamental conflict between two of our most successful theories of physics. General relativity, which describes gravity and the large-scale structure of spacetime, allows information to disappear into black holes and potentially be destroyed when they evaporate. Quantum mechanics, which governs the behavior of matter and energy at the smallest scales, insists that information must be conserved in all physical processes. Stephen Hawking himself initially believed that information was indeed destroyed in black hole evaporation, representing a fundamental breakdown of quantum mechanics in the presence of strong gravitational fields. This was a radical position, suggesting that our understanding of quantum mechanics would need to be modified when applied to situations involving gravity and black holes. However, many physicists found this conclusion deeply troubling. Quantum mechanics had been tested in countless experiments and had never been found to violate information conservation. The principle of information conservation is closely connected to the reversibility of physical laws and the conservation of probability in quantum systems. If information could be destroyed in black holes, it might call into question our entire understanding of how the quantum world works. Over the decades, several potential solutions to the paradox have been proposed. One possibility is that the Hawking radiation is not truly thermal, but contains subtle correlations that encode the information about what fell into the black hole. These correlations might be so faint and complex that they're essentially impossible to detect with any realistic measurement, but they would be sufficient to preserve information conservation in principle. Another proposal suggests that information doesn't actually cross the event horizon, but instead remains encoded on the black hole's surface throughout the evaporation process. According to this holographic principle, all the information about the black hole's interior is somehow encoded in the quantum state of the Hawking radiation being emitted from the vicinity of the event horizon. A more radical possibility is that the geometry of spacetime itself breaks down near black holes in ways that general relativity doesn't capture. If the event horizon isn't the smooth, empty boundary that classical relativity suggests, but instead has a rich quantum structure that can store and release information, then the information paradox might be resolved without violating either quantum mechanics or general relativity. Recent developments in theoretical physics, particularly in the study of quantum gravity and string theory, have suggested that the paradox might be resolved through the emergence of wormholes or quantum entanglement between the interior and exterior of black holes. These ideas propose that information is neither destroyed nor trapped, but rather is transferred through subtle quantum connections that preserve unitarity. The fundamental quantum mechanical principle that probabilities always add up to 1. In 2004, Stephen Hawking reversed his earlier position and conceded a famous bet with fellow physicists, acknowledging that information is probably conserved in black hole evaporation. However, the precise mechanism by which this conservation occurs remains one of the most active areas of research in theoretical physics, touching on fundamental questions about the nature of space, time, information, and reality itself. To truly appreciate the majesty of black hole evaporation, we must shift our perspective to cosmic time scales that stretch far beyond human experience. When we talk about a solar mass black hole taking 1067 years to evaporate, we're discussing a process so slow that it challenges our very conception of change and permanence in the universe. During the first phase of this evaporation, which would last for most of the black hole's lifetime, the process would be almost imperceptibly slow. The black hole would emit roughly 1 photon per second, not 1 photon per second per square meter of surface area, but literally just 1 photon per second from the entire black hole. These photons would have energies measured in microelectron volts, making them among the lowest energy particles in the universe. For comparison, visible light photons have energies measured in electron volts, millions of times more energetic than the typical Hawking radiation from a stellar mass black hole. Radio waves from a typical broadcast station carry more energy per photon than the radiation from such a black hole. Even the gentle thermal radiation from your own body at room temperature consists of photons that are vastly more energetic than those emitted by evaporating stellar mass black holes. This means that for the vast majority of its evaporation lifetime, a black hole would be essentially invisible against the background radiation of the universe. The cosmic microwave background, the afterglow of the Big Bang that fills all of space, with a temperature of about 2.7 degrees above absolute zero, is far hotter than the Hawking radiation from any black hole more massive than about 1014 kilograms, roughly the mass of a small mountain. As the universe continues to expand and cool, however, this background temperature will continue to drop. In about 1013 years, 1,000 times the current age of the universe, the cosmic microwave background will have cooled to the point where stellar mass black holes will finally be warmer than their surroundings and begin to evaporate faster than they grow. Even then, the evaporation would proceed at a glacial pace. For most of the black hole's remaining lifetime, it would lose mass so slowly that its size would remain essentially constant from any human perspective. The event horizon of a solar mass black hole has a radius of about 3 kilometers. After a trillion years of evaporation, it might have shrunk by less than the width of an atom. Only in the final stages of evaporation would the process accelerate noticeably. When the black hole had shrunk to about the mass of the Earth, it would still take another 1050 years to evaporate completely. When it reached the mass of a large mountain, roughly 1015 kilograms, it would have only about 1040 years left. And when it finally reached the mass of a small asteroid, about 1012 kilograms, it would have just 1030 years remaining. In its very final moments, when the black hole had shrunk to microscopic size, the evaporation would become explosive. A black hole with the mass of a proton would evaporate in about 10⁻40 seconds, releasing all of its remaining mass energy in a brilliant flash of gamma rays and exotic particles. This final explosion would be far more energetic than any nuclear weapon, despite coming from an object smaller than an atomic nucleus. Throughout this entire process, spanning time scales that dwarf even geological time, the black hole would serve as a perfect converter of gravitational mass into thermal radiation. It would take the highly ordered gravitational energy locked up in its intense spacetime curvature and slowly, patiently convert it into the most disordered form of energy possible, completely random thermal radiation, distributed uniformly in all directions. This process represents one of the most profound examples of the second law of thermodynamics in action on a cosmic scale. The black hole starts as a highly ordered, low-entropy object, all of its mass concentrated at a single point, creating maximum gravitational organization. Over cosmic time, it converts this order into maximum disorder, ending as a cloud of randomly distributed thermal radiation that will eventually spread throughout the universe, becoming part of the ever-growing sea of entropy that characterizes our expanding cosmos. The boundary of a black hole, the event horizon, is far more than just a simple spherical surface in space. From the perspective of quantum field theory, the event horizon is a dynamic, quantum mechanical boundary, where the very nature of space and time undergoes a subtle but profound transformation. Understanding the quantum properties of event horizons is crucial to grasping how Hawking radiation emerges and why black holes behave thermodynamically like hot objects. In classical general relativity, the event horizon is defined as the boundary beyond which nothing can escape to reach a distant observer. It's a coordinate-independent concept. Different observers might measure the location of the horizon differently, but they would all agree on which events can and cannot escape to infinity. The horizon itself is not made of matter or energy. It's purely a geometrical feature of curved spacetime. But quantum mechanics adds layers of complexity to this picture. In quantum field theory, the vacuum state, the state with the lowest possible energy, is not empty, but filled with quantum fluctuations. These fluctuations represent the fundamental uncertainty principle applied to fields. Even in empty space, quantum fields cannot have precisely zero value everywhere, because that would require knowing both the field value and its rate of change with perfect precision, which is forbidden by quantum mechanics. Near an event horizon, these quantum fluctuations behave differently than they do in flat spacetime. The extreme curvature of spacetime near the horizon creates what physicists call frame dragging effects, where the geometry of space itself appears to be flowing toward the black hole's center. This flowing geometry affects how quantum fields propagate and how virtual particles behave. From the perspective of a distant observer, the region just outside the event horizon appears to be filled with a warm quantum atmosphere, a thin layer of virtual particles that are constantly being created and destroyed by the curved spacetime geometry. Some of these virtual particles have just enough energy to escape to infinity, becoming real particles that carry energy away from the black hole. Others fall inward past the event horizon, carrying negative energy that reduces the black hole's mass. This quantum atmosphere has a temperature that depends on the surface gravity of the black hole, a quantity that measures how rapidly the gravitational field increases as you approach the horizon. For a non-rotating black hole, the surface gravity is inversely proportional to the black hole's mass, which is why smaller black holes are hotter than larger ones. The quantum atmosphere also has interesting properties related to the black hole's entropy. According to the holographic principle, one of the most important insights to emerge from string theory, all the information about the black hole's interior is somehow encoded on its two-dimensional event horizon surface. The entropy of the black hole, which measures how much information it contains, is proportional to the area of this surface, rather than its volume. This is profoundly different from ordinary thermodynamic systems, where entropy usually scales with volume. For a gas in a container, doubling the container's size doubles the entropy because there are twice as many places for the gas molecules to be. But for a black hole, doubling the mass increases the entropy by a factor of 4, because the event horizon's area scales as the square of the black hole's radius. This area law for black hole entropy suggests that the fundamental degrees of freedom, the basic units of information, associated with a black hole are located on its surface rather than in its interior. Each unit area of the event horizon, measured in units of the Planck length squared, about 10⁻66 square centimeters, corresponds to roughly 1 bit of information. For a solar mass black hole, this means the event horizon encodes about 1077 bits of information, more than the estimated information content of all the books ever written by humanity. The quantum properties of event horizons also lead to some counterintuitive effects. For instance, an observer falling through an event horizon would not experience anything special at the moment of crossing. The horizon would be completely invisible to them, but a distant observer watching the fall would see the falling observer slow down and fade away as they approached the horizon, their image becoming increasingly redshifted until it disappeared from view. This difference in perspective is related to the quantum entanglement between the interior and exterior of the black hole. Recent research in quantum gravity suggests that the vacuum state near a black hole is actually a highly entangled quantum state, with quantum correlations stretching across the event horizon. These correlations might be responsible for preserving information during the evaporation process, providing a potential resolution to the information paradox. The study of quantum properties of event horizons has also led to insights about the nature of spacetime itself. Some theories suggest that spacetime emerges from more fundamental quantum entanglement patterns, with event horizons serving as boundaries where different entanglement networks meet. In this view, the smooth geometry of general relativity would be an approximation that emerges from underlying quantum information processing. The radiation emitted by evaporating black holes is not a simple, uniform stream of identical particles. Instead, it's a complex symphony of different types of particles and radiation, each carrying away different amounts of energy and contributing to the black hole's gradual return to the quantum vacuum from which all matter and energy emerged. In the earliest phases of evaporation, when the black hole is still very massive and cold, the radiation consists almost entirely of photons, particles of light, with extremely low energies. These photons have wavelengths comparable to the size of the black hole itself, making them among the lowest frequency electromagnetic radiation possible. For a solar mass black hole, the typical photon would have a wavelength of about 6 kilometers and a frequency of about 50,000 hertz in the extremely low frequency radio band. These radio frequency photons are so low in energy that they carry away the black hole's mass incredibly slowly. Each photon removes only about 10⁻10 electron volts of mass energy from the black hole, roughly the amount of kinetic energy in a single molecule of air at room temperature. At this rate, it would take about 1067 years for the black hole to radiate away its entire mass, one radio photon at a time. As the black hole shrinks and its temperature increases, the spectrum of emitted radiation begins to include higher energy photons. When the black hole has evaporated down to about 1030 kilograms, roughly the mass of a large asteroid, its temperature would have increased to about 1 degree above absolute zero, and it would begin emitting microwave radiation, similar to the cosmic microwave background. When the black hole reaches a mass of about 10-20 kilograms, roughly the mass of a large mountain, its temperature would be about 100 degrees above absolute zero, and it would begin emitting infrared radiation. At this point, the black hole would actually be warm enough to melt ice, though it would still be far too small and dim to be detectable by any conceivable instrument. As evaporation continues and the black hole becomes even smaller and hotter, the radiation spectrum extends into visible light, then ultraviolet, then X-rays, and finally gamma rays. A black hole with the mass of the Moon would have a temperature of about 10 million degrees and would emit primarily X-rays. One with the mass of a large building would glow with gamma rays hot enough to power a star. But Hawking radiation is not limited to photons. As the black hole's temperature increases, it begins to emit other types of particles as well. When the temperature becomes comparable to the rest mass energy of electrons, about 0.5 million electron volts, the black hole begins to emit electron-positron pairs. At higher temperatures, it emits muons, pions, and eventually all the particles in the standard model of particle physics. In the final stages of evaporation, when the black hole has become microscopic but extraordinarily hot, it begins to emit exotic particles that we can barely create in our most powerful particle accelerators. Quarks and gluons, the fundamental building blocks of protons and neutrons, stream away from the dying black hole in jets of high-energy plasma. Neutrinos, those ghostly particles that barely interact with ordinary matter, pour out in vast numbers, carrying away energy at nearly the speed of light. The final moments of a black hole's life are truly spectacular on a quantum scale. When the black hole has shrunk to the Planck mass, about 2 × 10⁻⁸ kilograms, roughly the mass of a flea, its temperature reaches the Planck temperature of about 1032 degrees. At this point, the distinction between different types of particles begins to break down, and the black hole emits a democratic mixture of all possible particle types with roughly equal probability. The radiation from an evaporating black hole also has a distinctive statistical signature. Unlike the coherent light from a laser or the thermal radiation from an incandescent bulb, Hawking radiation follows what physicists call Planck distribution, the same statistical pattern followed by the radiation from any perfect blackbody. This means that if you could somehow collect and analyze the radiation from an evaporating black hole, you would find that the energy distribution of the photons follows a precise mathematical curve that depends only on the black hole's temperature. This thermal nature of the radiation is one of the most remarkable aspects of Hawking's discovery. It shows that black holes truly behave like thermodynamic objects, following the same statistical laws that govern steam engines, refrigerators, and living cells. The black hole doesn't remember what kind of matter fell into it originally. Whether it was hydrogen, iron, or antimatter, the radiation that emerges is always perfectly thermal, characterized only by its temperature and total energy output. However, recent theoretical work has suggested that the radiation might not be perfectly thermal after all. Subtle quantum correlations between the emitted particles might carry information about the black hole's interior, providing a potential solution to the information paradox. These correlations would be extraordinarily faint, much too weak to detect with any realistic technology. But they would be sufficient to preserve the fundamental principle of information conservation in quantum mechanics. To understand the true significance of black hole evaporation, we must place these cosmic vacuum cleaners in the broader context of our expanding, evolving universe. Black holes don't exist in isolation. They're embedded in a dynamic cosmos that itself is changing in profound ways over time scales that dwarf even the patient evaporation of the largest black holes. Our universe today is about 13.8 billion years old, and it's filled with the afterglow of the Big Bang, the cosmic microwave background radiation that maintains a temperature of about 2.7 degrees above absolute zero. This background radiation is currently much warmer than the Hawking radiation from any black hole, more massive than about 10-14 kilograms, which means that stellar mass and supermassive black holes are actually absorbing more energy from the cosmic background than they're emitting through Hawking radiation. This situation creates a fascinating cosmic race between two competing processes. On one hand, black holes are slowly trying to evaporate according to Hawking's mechanism. On the other hand, they're constantly absorbing photons from the cosmic microwave background, which tends to make them grow rather than shrink. Currently, the absorption process dominates, so black holes in our present universe are actually growing very slowly rather than evaporating. But the universe is expanding, and as it expands, it cools. The temperature of the cosmic microwave background is inversely proportional to the size of the universe. So as space continues to stretch, this background radiation becomes cooler and cooler. In about 10-13 years, 1,000 times the current age of the universe, the cosmic background will have cooled to the point where it's colder than the Hawking radiation from stellar mass black holes. At that point, these black holes will finally begin to evaporate faster than they grow. This transition marks the beginning of what cosmologists call the black hole era, a phase of cosmic evolution that will last far longer than the current stelliferous era, during which stars are being born and dying. The black hole era will be characterized by a universe filled primarily with black holes of various sizes, slowly evaporating in the growing darkness of an ever-expanding, ever-cooling cosmos. During the black hole era, the universe will be a very different place than it is today. The last stars will have burned out trillions of years earlier, leaving behind white dwarfs, neutron stars, and black holes as the only remnants of the once glorious stellar epoch. Galaxies will have evaporated as their constituent stars are either captured by central supermassive black holes or ejected into intergalactic space through gravitational interactions. The supermassive black holes that currently lurk at the centers of galaxies, with masses ranging from millions to billions of times that of our Sun, will become the dominant objects in the universe. These cosmic giants will take unimaginably long times to evaporate. The largest ones will persist for 10-100 years or more, slowly converting their mass into the gentlest possible form of thermal radiation. As these black holes evaporate, they will provide the only sources of energy in an otherwise cold, empty universe. Their Hawking radiation will create brief, local increases in temperature and entropy, driving any remaining physical processes in a cosmos that has otherwise reached near-perfect thermal equilibrium. In a sense, evaporating black holes will serve as the universe's final energy sources, the last flickering candles in an otherwise dark and silent cosmos. The radiation from these evaporating black holes will also play a crucial role in the universe's ultimate fate. Each photon of Hawking radiation carries momentum as well as energy. And over cosmic time scales, the pressure from this radiation will contribute to the universe's continued expansion. Black holes, which began as the ultimate gravitational attractors, will end their lives by contributing to the very expansion that carries matter and energy ever further apart. During the final phases of black hole evaporation, when the largest black holes have shrunk to stellar masses and below, The universe will experience a series of spectacular fireworks as these cosmic time bombs reach their explosive endpoints. Each final evaporation will release the energy equivalent of billions of hydrogen bombs in a brief, brilliant flash of high-energy particles and radiation. These explosions will be scattered randomly throughout space and time, providing brief moments of intense activity in an otherwise quiescent universe. After the last black hole has evaporated, the universe will enter its final phase, the heat-death era, characterized by maximum entropy and minimum organization. All the mass and energy that once formed stars, planets, and black holes will have been converted into a thin, cold gas of photons, leptons, and other stable particles, distributed uniformly throughout an ever-expanding space. The universe will have reached a state of perfect thermal equilibrium, with no remaining sources of free energy to drive any physical processes. Yet even this seemingly final state may not be permanent. Quantum mechanics allows for the possibility of random fluctuations that could, over truly astronomical timescales, spontaneously organize matter and energy into complex structures once again. In 1056 years, a number so large that it's difficult even to express, random quantum fluctuations might create new universes, new Big Bangs, and new cycles of cosmic evolution. Black hole evaporation, in this view, would be just one phase in an eternal cycle of cosmic death and rebirth. One of the most beautiful aspects of Hawking's discovery is that the physics underlying black hole evaporation appears in many other contexts, from the flow of water over a waterfall to the behavior of sound waves in moving fluids. These analog systems allow physicists to study Hawking radiation in laboratory settings, providing insights into the quantum mechanics of curved spacetime that would be impossible to obtain by observing real black holes. The most famous of these analog systems involves the flow of water in a stream or channel. When water flows faster than the speed of surface waves, a condition known as supercritical flow, it creates what's called a white hole horizon. Surface waves generated downstream of this horizon cannot propagate back upstream against the flow, just as light cannot escape from inside a black hole's event horizon. Near such a water horizon, quantum fluctuations in the water's surface behave similarly to quantum field fluctuations near a black hole. The flowing water creates pairs of surface waves, with one member of each pair swept downstream by the flow, while the other propagates upstream away from the horizon. This process should produce a steady stream of surface waves that carry energy away from the horizon, the analog of Hawking radiation. The temperature of this analog Hawking radiation depends on the gradient of the water flow near the horizon, just as the temperature of real Hawking radiation depends on the surface gravity of the black hole. Steeper gradients produce higher temperature radiation, while gentler gradients produce cooler radiation. The mathematical description of this process is remarkably similar to Hawking's original calculation for black holes, despite involving completely different physics. Similar analog systems can be created using sound waves in moving fluids. When a fluid flows faster than the local speed of sound, it creates a sonic horizon beyond which sound waves cannot propagate backward against the flow. Quantum fluctuations in the fluid's density and pressure near such horizons should produce pairs of phonons quantized sound waves, with one member of each pair escaping to infinity, while the other falls into the supersonic region. These sonic analogs have actually been observed in laboratory experiments using ultra-cold atomic gases called Bose-Einstein condensates. In these systems, the atoms behave more like waves than particles, and disturbances in the atomic density propagate like sound waves. By creating supersonic flow in these atomic clouds, physicists have successfully observed the analog of Hawking radiation, confirming many of the theoretical predictions about the process. Other analog systems include light waves in nonlinear optical materials, electromagnetic waves in moving dielectric media, and even mechanical vibrations in crystalline solids. Each of these systems provides a different perspective on the underlying physics of Hawking radiation, helping to illuminate different aspects of the phenomenon and test various theoretical predictions. Perhaps most remarkably, some of these analog systems allow physicists to study analogs of the black hole information paradox. In fluid systems, the analog of information might be the detailed pattern of surface waves or density fluctuations. The question becomes, if you create an analog black hole and let it evaporate by emitting analog Hawking radiation, can you reconstruct the initial information from the final radiation state? Recent experiments with analog black holes have suggested that information can indeed be recovered, at least in principle, but only by making extraordinarily precise measurements of subtle correlations in the analog Hawking radiation. This supports theoretical arguments that real black holes preserve information during evaporation, but in such a subtle way that the information would be practically impossible to extract from real Hawking radiation. The study of analog black holes has also revealed new insights into the role of quantum entanglement in the Hawking radiation process. In many analog systems, the pairs of quasiparticles created near the horizon are quantum entangled. Their properties are correlated in ways that cannot be explained by classical physics. This entanglement appears to be crucial for information preservation, providing a quantum link between the radiation that escapes to infinity and the information that falls into the black hole. These analog systems remind us that the physics of black hole evaporation is not unique to gravity and general relativity, but rather reflects deep, universal principles about how quantum fields behave in any system with appropriate boundary conditions. They suggest that Hawking radiation is a fundamental feature of quantum field theory that appears whenever classical information becomes inaccessible due to causal horizons, regardless of whether those horizons are created by gravity, fluid flow, or any other physical mechanism. Despite more than 4 decades of theoretical development since Hawking's original discovery, the direct detection of Hawking radiation from real black holes remains one of the most challenging problems in observational physics. The radiation is so incredibly faint, and the background interference so overwhelming, that no current or planned instrument can hope to detect it from stellar mass or supermassive black holes. The fundamental challenge is one of signal versus noise. A solar mass black hole emits roughly 1 microwave photon per second, with an energy of about 10^-10 electron volts. To put this in perspective, the cosmic microwave background that fills all of space contains about 400 million photons per cubic centimeter, each carrying about 1,000 times more energy than a typical Hawking photon. Detecting Hawking radiation against this background would be like trying to hear a whisper in a thunderstorm. The situation is even more challenging for supermassive black holes, which emit even lower energy photons at even slower rates. The supermassive black hole at the center of our galaxy, Sagittarius A, has a mass about 4 million times that of the Sun and emits roughly 1 photon every 4 million seconds, with an energy so low that it would take billions of such photons to equal the energy of a single radio photon from a typical broadcast station. However, there are several indirect ways that Hawking radiation might be detected or constrained by future observations. One possibility involves primordial black holes, hypothetical black holes, that might have formed in the early universe from the gravitational collapse of dense regions of matter. Unlike the stellar mass black holes we observe today, primordial black holes could have a wide range of masses, including some small enough to be evaporating rapidly in the present epoch. A primordial black hole with an initial mass of about 10-12 kilograms would be evaporating explosively right now, having reached the final stages of its 13.8 billion year evaporation process. Such a black hole would emit high-energy gamma rays at a rate detectable by space-based gamma-ray telescopes. The distinctive spectrum and time signature of the final evaporation explosion would provide unmistakable evidence for Hawking radiation. Several gamma-ray observatories, including the Fermi Gamma Ray Space Telescope and ground-based atmospheric Cherenkov telescopes, have searched for these distinctive evaporation signatures. So far, no convincing detections have been made, which places upper limits on the number density of primordial black holes in our cosmic neighborhood. These limits constrain theories about the early universe and the formation of structure in the first moments after the Big Bang. Another approach involves studying the environment around known black holes for evidence of the subtle effects of Hawking radiation. While the radiation itself may be undetectable, it might have observable consequences for the matter and radiation in the black hole's vicinity. For instance, Hawking radiation might create small but measurable changes in the polarization of light from matter falling into black holes. Or it might produce distinctive signatures in the gravitational waves emitted during black hole mergers. The recent direct detection of gravitational waves by the LIGO and Virgo observatories has opened up new possibilities for studying black hole physics. Future gravitational wave detectors, with improved sensitivity and broader frequency ranges, might be able to detect subtle modifications to gravitational wave signals caused by Hawking radiation. These modifications would be extraordinarily faint, but they might be detectable in the most precisely measured signals from nearby black hole mergers. Space-based gravitational wave detectors, such as the proposed LISA mission, will be sensitive to different frequency ranges than ground-based detectors, and might be able to study the gravitational wave signatures of smaller black holes, including potentially primordial ones. If primordial black holes exist in the mass range that LISA can detect, their evaporation signatures might be observable as transient gravitational wave sources. There's also the intriguing possibility of detecting Hawking radiation from black holes created artificially in high-energy particle physics experiments. Some theories predict that if extra dimensions of space exist beyond the familiar 3 dimensions, it might be possible to create microscopic black holes in particle accelerators like the Large Hadron Collider. These microscopic black holes would evaporate almost instantaneously, but their evaporation products might be detectable as distinctive showers of particles in the accelerator's detectors. While no evidence for such microscopic black holes has been found in current experiments, future, more powerful accelerators might be able to reach the energy scales where black hole production becomes possible. The detection of evaporating microscopic black holes would provide direct confirmation of Hawking's theoretical predictions, and would also reveal information about the structure of space at the smallest scales. Perhaps most intriguingly, advances in quantum technology might eventually make it possible to create and study analog black holes with sufficient precision to observe analog Hawking radiation directly. While these systems wouldn't involve real gravity or real black holes, they would be governed by the same mathematical principles that describe Hawking radiation, providing a way to test theoretical predictions in controlled laboratory conditions. The philosophical implications. Time, impermanence, and cosmic evolution, the discovery that black holes evaporate carries profound philosophical implications that extend far beyond the technical details of quantum field theory and general relativity. It touches on fundamental questions about the nature of time, the meaning of permanence, and our place in an evolving cosmos that operates on scales both vastly larger and vastly longer than human experience. Perhaps most fundamentally, Hawking radiation demonstrates that nothing in our universe is truly permanent. Even the most massive, most stable objects, we know black holes, that could survive the complete evaporation of all the stars in the universe, eventually return their borrowed matter and energy to the cosmic background from which they emerged. This revelation places black hole evaporation alongside other great discoveries in physics that have revealed the deep impermanence underlying apparent stability. The radioactive decay of atomic nuclei, the expansion of the universe, and the heat death predicted by thermodynamics. Yet this impermanence operates on time scales so vast that they challenge our intuitive understanding of change and duration. When we say that a solar mass black hole will evaporate in 1067 years, we're talking about a span of time that's incomprehensibly longer than any human reference point. If the entire history of the universe, from the Big Bang to the present, were compressed into a single second, the evaporation time of such a black hole would still be longer than the age of the universe, by a factor that itself requires scientific notation to express. This extreme separation of time scales raises profound questions about the nature of time itself. From a human perspective, black holes appear eternal and unchanging cosmic landmarks that persist unchanged while stars are born and die, while galaxies collide and merge, while entire species evolve and go extinct. Yet, from the perspective of the black holes themselves, their evaporation is a natural and inevitable process, as fundamental as the ticking of a cosmic clock. The process of black hole evaporation also embodies one of the most profound principles in all of physics, the second law of thermodynamics, which states that the entropy of an isolated system can never decrease. Black holes represent gravitational order, all of their mass concentrated at a single point, creating maximum organization in spacetime. Through Hawking radiation, this gravitational order is slowly converted into thermal disorder, random photons scattered uniformly throughout space. This transformation from order to disorder plays out on the largest possible scales, involving not just individual particles or even solar systems, but the fundamental structure of spacetime itself. Black holes begin as the most organized objects possible in general relativity, and end as the most disorganized form of energy possible, completely random thermal radiation. They serve as cosmic engines of entropy production, taking the universe step by step toward its ultimate fate of maximum disorder and minimum organization. Yet, within this seemingly pessimistic picture of cosmic evolution toward heat death, there's a strange kind of beauty and hope. The evaporation of black holes represents the universe's memory of every star that ever shone, every planet that ever formed, every complex structure that ever arose from the primordial chaos following the Big Bang. In a sense, Hawking radiation is the cosmos slowly telling the story of its own evolution, converting the gravitational fossil record of cosmic history into gentle whispers of thermal radiation. The information paradox adds another layer of philosophical complexity to this picture. If information is truly fundamental and cannot be destroyed, then the thermal radiation from evaporating black holes must somehow encode every detail of everything that ever fell into them. This would mean that the universe possesses a perfect memory, that every book ever written, every thought ever thought, Every pattern of matter and energy that ever existed is somehow preserved in the subtle correlations between the photons that emerge from dying black holes. This possibility suggests a kind of cosmic conservation law for information that parallels the conservation of mass and energy. Just as energy cannot be created or destroyed, but only transformed from one form to another, information might be conserved in transformations so subtle and complex that they're beyond our current ability to detect or decode. The universe would be not just a vast machine converting order into disorder, but also a cosmic library preserving every detail of its own history in forms we're only beginning to understand. The study of black hole evaporation has also revealed deep connections between seemingly unrelated areas of physics, from quantum mechanics to thermodynamics to information theory. These connections suggest that the universe operates according to principles that are far more unified and elegant than our everyday experience might suggest. The same mathematical structures that describe the gentle evaporation of black holes also appear in the behavior of quantum computers, the flow of heat through materials, and the processing of information in biological systems. Perhaps most remarkably, the physics of black hole evaporation suggests that space and time themselves might not be fundamental features of reality, but rather emergent properties that arise from more basic quantum information processes. In this view, the smooth spacetime of general relativity would be like the surface of a fluid, apparently continuous from a distance, but actually composed of discrete quantum elements at the smallest scales. This possibility opens up entirely new ways of thinking about the nature of reality itself. If spacetime emerges from quantum information, then the universe might be fundamentally computational in nature. A vast information processing system where black holes serve as cosmic computers, slowly processing and outputting the information they contain over time scales that span the entire future evolution of the cosmos. There's a remarkable beauty in the mathematical description of black hole evaporation that speaks to the deep elegance underlying the physical laws that govern our universe. The key equation describing Hawking radiation is both simple and profound. The temperature of a black hole is inversely proportional to its mass, with the proportionality constant depending only on fundamental constants of nature. Mathematically, we can write this as T equals letter 210 FC 3/8 pi g mkb, where T is the temperature, m is the black hole's mass, and the other symbols represent fundamental constants. Letter 210F is Planck's reduced constant quantum mechanics. C is the speed of light relativity. G is Newton's gravitational constant gravity. And Kb is Boltzmann's constant thermodynamics. This single equation brings together concepts from all the major areas of physics, showing how quantum mechanics, relativity, gravity, and thermodynamics unite in the phenomenon of black hole evaporation. The appearance of these fundamental constants in the Hawking temperature formula is more than just mathematical convenience. It reveals deep connections between different areas of physics that were once thought to be completely separate. The presence of Planck's constant shows that black hole evaporation is fundamentally a quantum mechanical process. The speed of light appears because the physics near black holes is inherently relativistic. Newton's gravitational constant is there because the entire phenomenon depends on the strong gravitational fields that create black holes in the first place. And Boltzmann's constant appears because the radiation has the statistical properties of thermal equilibrium. The inverse relationship between temperature and mass creates the runaway evaporation process that characterizes the final stages of black hole evolution. As the black hole loses mass through radiation, its temperature increases, which causes it to radiate faster, which causes it to lose mass faster, which increases its temperature even more. This positive feedback loop is described by a differential equation, whose solution shows that the black hole's mass decreases as the cube root of the remaining time until complete evaporation. This mathematical relationship means that black holes spend most of their evaporation lifetime at nearly constant mass and temperature, with the evaporation rate increasing dramatically only in the final phases. For a solar mass black hole, 99.9% of the evaporation time is spent losing the first 90% of the mass. The remaining 10% of the mass is lost in just 0.1% of the total evaporation time, in an accelerating cascade that ends in a final explosive release of energy. The entropy of a black hole follows an even more beautiful mathematical relationship. S equals K back 3/4 letter 210 Fg, where A is the area of the event horizon. This formula, known as the Bekenstein-Hawking entropy, shows that black hole entropy is proportional to area rather than volume, a relationship that has profound implications for our understanding of information and the nature of space itself. The area law for black hole entropy suggests that the maximum amount of information that can be stored in any region of space is proportional to the area of that region's boundary, not its volume. This holographic principle implies that all the information about a black hole's interior is somehow encoded on its two-dimensional surface, like a hologram that contains a three-dimensional image. The mathematical consistency of black hole thermodynamics also leads to precise relationships between temperature, entropy, and energy that mirror the laws of ordinary thermodynamics. The first law of black hole thermodynamics states that changes in a black hole's mass are related to changes in its area and angular momentum, in exactly the same way that changes in the internal energy of a gas are related to changes in entropy and other thermodynamic variables. These mathematical relationships have a kind of inevitability about them. Once you accept the basic principles of quantum mechanics and general relativity, the existence of Hawking radiation and the thermodynamic properties of black holes follow almost automatically from the mathematics. This suggests that black hole evaporation is not an accidental consequence of our particular physical laws, but rather a fundamental feature that would appear in any universe governed by quantum mechanics and gravity. The mathematics also reveals subtle symmetries and conservation laws that might not be obvious from physical intuition alone. For instance, the total amount of information that emerges in Hawking radiation over the complete evaporation of a black hole is exactly equal to the maximum amount of information that could have been stored in the black hole, providing a precise mathematical expression of information conservation. Recent developments in string theory and quantum gravity have revealed even deeper mathematical structures underlying black hole evaporation. These theories suggest that the apparent randomness of Hawking radiation might actually be an illusion, that the radiation carries subtle correlations and patterns that encode all the information about the black hole's interior in a form so complex that it appears random to any finite observer. The mathematics of these quantum correlations involves sophisticated concepts from quantum information theory, including quantum error correction, quantum entanglement, and quantum computational complexity. These same mathematical tools are used to design quantum computers and to understand how biological systems process information, suggesting deep connections between black hole physics and other areas of science and technology. In the grand scheme of cosmic evolution, Black holes serve as the universe's ultimate recycling centers, cosmic engines that take highly organized gravitational energy and slowly, patiently convert it into the most disorganized form possible, random thermal radiation. This process plays a crucial role in the universe's journey toward maximum entropy, serving as a bridge between the organized structures of the stellar era and the uniform thermal equilibrium of the far future. When a massive star collapses to form a black hole, an enormous amount of gravitational binding energy is released, energy that was stored in the original configuration of matter spread throughout the star's volume. Most of this energy is carried away by neutrinos and gravitational waves during the collapse itself, but a significant fraction remains locked up in the black hole's intense gravitational field. The black hole represents a highly ordered state, all of its mass concentrated at a single point, creating maximum possible curvature in the surrounding spacetime. From a thermodynamic perspective, this gravitational organization represents very low entropy. The black hole knows exactly where all of its mass is located at the central singularity, and the spacetime geometry around it is perfectly determined by just a few parameters: the mass, electric charge, and angular momentum. This is in stark contrast to a gas at thermal equilibrium, where the positions and velocities of particles are randomly distributed and constantly changing. Through the process of Hawking radiation, black holes slowly convert this gravitational order into thermal disorder. Each photon that escapes to infinity carries away a tiny amount of the black hole's organized mass energy and adds it to the growing sea of random thermal radiation that fills the universe. Over time, scales that dwarf the current age of the cosmos. This process transforms the highly ordered gravitational field of the black hole into the most disordered possible state, a uniform distribution of low-energy photons. This transformation follows the fundamental arrow of time encoded in the second law of thermodynamics. The universe began in a highly organized state, all of its matter and energy concentrated in the extremely low entropy conditions of the Big Bang. Over cosmic time, this initial organization has been steadily converted into increasingly disordered forms. First into the hydrogen and helium that formed the first stars, then into the heavier elements created by stellar nucleosynthesis, then into the planets and complex molecules that allowed life to emerge. Black holes represent one of the final stages in this cosmic progression toward maximum entropy. They are the gravitational tombs of massive stars, the repositories of the organized energy that once powered stellar fusion and illuminated the cosmos. Through Hawking radiation, even these final monuments to gravitational order eventually surrender their energy to the universal tendency toward thermal equilibrium. The rate at which this entropy conversion occurs is incredibly slow for the black holes that exist in our current universe, but it's also inexorable. Every photon of Hawking radiation increases the universe's total entropy by a tiny amount, contributing to the cosmic accounting that tracks the universe's progress toward heat death. In the far future, when all the stars have burned out and the universe has cooled to near absolute zero, the gentle whisper of Hawking radiation from evaporating black holes will represent one of the last sources of entropy production in the cosmos. Yet this process of gravitational decay also serves a kind of cosmic justice. The matter that falls into black holes throughout their lifetimes, from the stellar material that formed them originally to the gas and dust they accrete over billions of years, is not permanently lost to the universe. Instead, it's slowly returned as thermal radiation, rejoining the cosmic background and becoming available to participate in whatever physical processes remain possible in the cold, expanded universe of the far future. In this sense, black holes are cosmic savings accounts, temporarily storing matter and energy in gravitational form, and then slowly releasing it back to the universe with interest. The interest, in this case, is the conversion of organized gravitational energy into disorganized thermal energy, contributing to the universe's inexorable march toward maximum entropy. The timescales involved in this cosmic recycling program are so vast that they challenge our ability to comprehend them meaningfully. A stellar mass black hole will spend 1067 years slowly converting its mass back into thermal radiation, a time so long that if the entire history of the universe, from the Big Bang to the heat death, were compressed into a single human lifetime, the evaporation of one black hole would still take billions of times longer than the entire history of human civilization. During this unimaginably long process, the black hole serves as a cosmic memory device, storing information about the matter that formed it and fell into it over its lifetime. If information is truly conserved in the evaporation process, then the Hawking radiation that emerges carries with it the encoded history of every star that contributed to the black hole's formation, every planet that was consumed during galactic mergers, every complex molecule that fell past the event horizon. This information would be encoded in quantum correlations so subtle and complex that they would be effectively impossible to decode. But its presence would ensure that nothing that ever existed is truly lost. The universe would maintain a perfect, if inaccessible, record of its own history, written in the language of quantum entanglement and statistical correlations between the photons that emerge from evaporating black holes. As we journey forward through cosmic time, far beyond the familiar epoch of stars and galaxies, we enter a universe transformed by the patient work of black hole evaporation. This is a cosmos operating on timescales so vast that the entire history of stars, from the formation of the first protostars, just a few 100 million years after the Big Bang, to the death of the last red dwarf, some 100 trillion years in the future, represents just the briefest prologue to the main story of cosmic evolution. In this far future universe, perhaps 1040 years from now, the last stars have long since exhausted their nuclear fuel and faded to cold, dark remnants. The once brilliant galaxies have either fallen into their central supermassive black holes or had their stars scattered into the growing emptiness of intergalactic space by gravitational encounters. What remains is a cosmos populated primarily by stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling toward the absolute zero temperature of empty space. But even these seemingly eternal objects are not permanent. The white dwarfs, those Earth-sized stellar corpses with masses comparable to our Sun, will eventually crystallize into cosmic diamonds as they cool. But even they are not immune to the quantum processes that govern matter at its most fundamental level. Through processes like proton decay, if it occurs, or quantum tunneling through energy barriers, even these crystallized stellar remnants will eventually dissolve back into their constituent particles, adding their mass energy to the thin soup of radiation and fundamental particles that fills the expanding universe. It's during this unimaginably distant epoch that black holes truly come into their own as the dominant sources of energy and entropy production in the universe. While stellar mass black holes remain cold and nearly inert, the supermassive black holes that once anchored the centers of galaxies begin to show the first signs of noticeable evaporation. These gravitational giants, with masses ranging from millions to billions of times that of our Sun, will have spent tens of billions of years slowly accreting matter from their surroundings. But in the empty universe of the far future, they finally begin to lose mass faster than they gain it. Even then, the process remains incredibly slow. A supermassive black hole with 1 billion solar masses will take approximately 1098 years to evaporate completely. A number so large that if you wrote it out in ordinary decimal notation, it would require more digits than there are atoms in the observable universe today. For most of this time, the black hole's evaporation is imperceptible, emitting perhaps one radio frequency photon every few years, adding infinitesimal amounts of thermal energy to the cold, empty space around it. Yet over these cosmic time scales, even such gentle processes can have profound cumulative effects. The thermal radiation from evaporating supermassive black holes will provide the primary source of energy for any physical processes that can still occur in the cold universe of the far future. This radiation will drive the random motion of particles, power the occasional chemical reactions between atoms scattered through space, and provide the energy needed for quantum processes that might spontaneously organize matter into more complex structures. In a universe approaching thermal equilibrium, where the temperature difference between different regions is measured in billionths of a degree, the gentle warmth from an evaporating black hole represents a significant source of free energy. Just as life on Earth ultimately depends on the nuclear fusion occurring in the sun's core, any form of information processing or organized activity in the far future universe might depend on the slow conversion of gravitational mass into thermal energy that occurs in evaporating black holes. The final phases of black hole evaporation will provide moments of intense activity scattered randomly throughout the otherwise quiet cosmos. When a supermassive black hole finally shrinks to stellar mass, it still has trillions of years of gentle evaporation ahead of it. But as it continues to lose mass and increase in temperature, the character of its radiation gradually changes from soft radio waves to microwaves, then to infrared light, visible light, and finally to high-energy gamma rays. During its final million years, a once supermassive black hole that has evaporated down to the mass of a mountain will shine like a star, pumping out more energy per second than our sun. In its final second of existence, when it has shrunk to microscopic size, it will release the energy equivalent of millions of hydrogen bombs in a brilliant flash of particles and radiation that will briefly illuminate a small region of the otherwise dark universe. These final evaporation events will be scattered randomly through space and time, like cosmic fireworks exploding in the infinite darkness. Each explosion will represent the end of a story that began billions of years earlier with the collapse of a massive star, continued through epochs of galactic evolution and stellar death, and finally concluded with the slow conversion of gravitational mass into thermal radiation. Between these explosive endpoints, the universe will be filled with black holes of all sizes slowly evaporating at different rates. Stellar mass black holes will be in their early phases of evaporation, still cold and emitting only the softest radio waves. Intermediate mass black holes will be warmer, contributing infrared and visible light to the cosmic background. The smallest black holes will be hot and bright, their high-energy radiation providing brief oases of warmth and activity in the cold cosmos. This epoch represents a kind of cosmic Indian summer, a period of gentle decline that lasts far longer than the vigorous activity of the stellar era that preceded it. While the universe will be far colder and emptier than it is today, it will not be completely devoid of energy and activity. The slow evaporation of black holes will provide a trickle of energy that could, in principle, support exotic forms of information processing, and even life adapted to the extreme conditions of deep time. The study of this far future epoch has inspired speculation about civilizations that might survive into the black hole era. Powered by the gentle energy from evaporating black holes and operating on time scales that dwarf biological evolution, such civilizations would need to be incredibly patient and efficient, conserving energy and information over periods longer than the current age of the universe. They might exist as patterns of information encoded in quantum fields, occasionally becoming active when sufficient energy becomes available from nearby evaporating black holes. Recent developments in quantum information theory have revealed that black holes might be understood not just as gravitational objects or thermodynamic systems, but as cosmic information processors, quantum computers operating on scales and time frames that dwarf any conceivable human technology. This perspective has revolutionized our understanding of what black holes are and what they do, suggesting that the evaporation process might represent the universe's most sophisticated form of quantum computation. The key insight comes from recognizing that the area law for black hole entropy, the fact that entropy scales with surface area rather than volume, is exactly what you would expect if black holes were storing information in quantum form at the fundamental Planck scale. Each unit of Planck area on the event horizon, roughly 10⁻66 square centimeters, appears to store approximately 1 bit of quantum information. For a solar mass black hole, this means the event horizon encodes about 1077 bits more information than could be stored in all the computer memories ever built by human civilization. This information storage capacity suggests that black holes might be natural quantum computers, with their event horizons serving as quantum memory banks and their evaporation process serving as a form of quantum computation. From this perspective, Hawking radiation isn't just thermal noise, but rather the output of a cosmic quantum calculation that has been running for the entire lifetime of the black hole. The computation performed by an evaporating black hole would be unlike any classical computer program. Instead of following a predetermined sequence of logical operations, the black hole would be exploring all possible quantum states simultaneously through the process of quantum superposition. The Hawking radiation would represent the probabilistic output of this quantum calculation, with each photon carrying information about the quantum computation occurring at the event horizon. This quantum computational view helps explain why Hawking radiation appears thermal from the perspective of any external observer. Quantum computations that explore exponentially large numbers of possibilities simultaneously often produce outputs that appear random to classical observers, even though they contain deep patterns and correlations that encode the results of the quantum calculation. The information paradox takes on new meaning from this perspective. Instead of being a problem about information loss, it becomes a question about quantum error correction. How does the black hole's quantum computer ensure that information is preserved even as it's being processed and output through Hawking radiation? Recent research suggests that black holes might employ sophisticated quantum error correction codes, similar to those being developed for human-built quantum computers, to protect information from decoherence and loss. These quantum error correction mechanisms would involve complex patterns of quantum entanglement between the black hole's interior and the Hawking radiation being emitted from its surface. The information would be encoded redundantly across many different quantum degrees of freedom, so that even if some of the information is lost or corrupted, the original data can still be recovered from the remaining correlations. The time scales involved in this quantum computation are truly staggering. A solar mass black hole would spend 1067 years processing whatever information fell into it during its formation and subsequent evolution. This represents a quantum calculation running continuously for a period longer than the universe has existed by a factor of 1057. A computational marathon that makes the most ambitious human supercomputing projects look like brief calculations. During this enormous computation, the black hole would be exploring quantum possibilities and correlations on a scale that's difficult to comprehend. Each quantum state of the system would be superposed with every other possible state, creating a quantum computer with more qubits than there are atoms in the observable universe. The computational power of such a system would be truly cosmic in scope. The output of this computation, the Hawking radiation, would carry information encoded in quantum correlations so subtle and complex that they would be effectively unreadable to any classical observer. But to a sufficiently advanced quantum computer, this radiation might contain incredibly rich and detailed information about the quantum state of everything that ever fell into the black hole. This quantum information perspective has also shed new light on the connections between black holes and quantum entanglement. The interior and exterior of a black hole appear to be connected by quantum entanglement patterns that span the event horizon, creating what physicists call Einstein-Rosen bridges or quantum wormholes. These entanglement connections might be what allows information to be preserved during the evaporation process, even though it cannot escape through classical means. The study of black holes as quantum computers has also inspired new approaches to building quantum computers here on Earth. Techniques developed to understand quantum error correction in black holes are being applied to design more robust quantum computing systems that can maintain quantum coherence for longer periods and perform more complex calculations. Perhaps most remarkably, this quantum computational view suggests that the universe itself might be understood as a vast quantum computer, with black holes serving as some of its most powerful processors. The evaporation of black holes would then represent the universe gradually computing its own future evolution, with each quantum process contributing to a cosmic calculation that determines the ultimate fate of matter, energy, and information in our cosmos. There's something deeply poetic about the way black holes return their borrowed matter to the universe, not through violent explosion or dramatic collapse, but through the gentlest possible whisper of thermal radiation. Like cosmic poets writing their stories in the language of quantum mechanics, black holes compose their final verses over time scales that stretch the very meaning of patience. Each photon, a carefully chosen word in an epic that spans the entire future history of the universe. The metaphor of poetry is more than just literary flourish. There's a real sense in which Hawking radiation represents the universe speaking to itself, telling the story of its own evolution through the medium of quantum field theory. Each photon that escapes from a black hole carries with it information about the matter that formed the black hole, the stars that died to create it, and the complex history of gravitational collapse and accretion that shaped its evolution. This information is encoded not in the obvious properties of the radiation, its energy, frequency, or direction, but in the subtle quantum correlations between different photons, correlations so delicate that they can only be read by observers with perfect knowledge of quantum mechanics and unlimited computational resources. In effect, the universe is writing its autobiography in a language so complex that only the universe itself can fully understand it. The rhythm of this cosmic poetry follows the mathematical harmonies discovered by Hawking and his colleagues. The temperature of a black hole's radiation beats in time with its mass, following the precise inverse relationship that connects quantum mechanics to gravity. As the black hole shrinks, its thermal voice rises in pitch, like a cosmic singer gradually ascending through octaves of electromagnetic radiation. From radio waves to microwaves, to visible light to gamma rays. The temporal structure of black hole evaporation also has a poetic cadence. Most of the black hole's lifetime is spent in quiet contemplation, emitting soft radiation at an almost imperceptible rate. Then, in a brief final stanza that lasts only a tiny fraction of its total existence, the evaporation accelerates into a crescendo of high-energy particles and intense radiation. It's as if the black hole spends eons carefully considering its words, then delivers its final message in a burst of brilliant eloquence. This pattern, long periods of gentle activity, punctuated by brief moments of intense creativity, is reminiscent of how human poets work, spending long periods in quiet observation and reflection, then producing their insights in concentrated bursts of creative expression. The universe, through its black holes, seems to follow a similar creative process, taking cosmic time to process and understand its own experiences before expressing them through the medium of Hawking radiation. The democratic nature of this radiation also has poetic resonance. Unlike the violent emissions from quasars or gamma ray bursts, which depend on the specific details of magnetic fields and plasma physics, Hawking radiation is universal. Every black hole, regardless of how it formed or what fell into it, emits radiation with exactly the same statistical properties. Perfect thermal radiation characterized only by temperature. This universality suggests that all black holes, despite their individual histories, ultimately speak the same cosmic language. Yet within this universal language, each black hole tells its own unique story. The subtle quantum correlations in its Hawking radiation encode the specific history of that particular black hole. Which stars collapsed to form it, what matter fell into it over its lifetime, how it interacted with its cosmic environment. These details are written in quantum ink, invisible to classical observers. But they're there nonetheless, preserving the individuality of each black hole, even as it speaks in the universal tongue of thermal radiation. The connection between black hole evaporation and information theory adds another layer to this poetic interpretation. If information is truly conserved during evaporation, then every black hole is simultaneously author and archive, creating new thermal radiation while preserving perfect records of everything that contributed to its existence. The universe uses black holes as cosmic libraries, storing the complete history of stellar evolution and galactic dynamics in quantum form, then slowly reading out this information through the process of Hawking radiation. This preservation of information across cosmic time scales means that nothing that ever existed is truly forgotten. Every star that ever shone, every planet that ever formed, every complex molecule that ever participated in the chemistry of life, all of these leave traces in the quantum correlations of Hawking radiation. The universe maintains a perfect memory of its own history, written in the most fundamental language possible, the language of quantum entanglement and statistical mechanics. The mathematical beauty of the equations governing black hole evaporation also contributes to their poetic character. The Hawking temperature formula brings together fundamental constants from quantum mechanics, relativity, gravity, and thermodynamics in a single elegant expression. It's as if the universe has distilled the essence of all its physical laws into one perfect equation that describes how gravitational order transforms into thermal chaos. This mathematical poetry extends to the geometrical aspects of black hole physics. The event horizon is not a physical surface, but a boundary in spacetime itself, a place where the geometry of reality becomes so curved that light itself cannot escape. The evaporation process gradually reduces this curvature, slowly returning the warped spacetime around the black hole to the flat geometry of empty space. In geometric terms, black hole evaporation is the universe's way of healing the wounds in spacetime left by gravitational collapse, gradually smoothing out the extreme curvatures created by massive stars. As we near the end of our journey through the quiet mysteries of black hole evaporation, let us settle into the peaceful realization that even the most permanent-seeming objects in our universe are part of a gentle, ongoing transformation, like autumn leaves slowly returning their borrowed nutrients to the soil from which they grew. Black holes patiently give back their mass and energy to the cosmic background, participating in the universe's grand cycle of organization and dissolution. The story we've explored tonight touches on some of the deepest questions in all of science: the nature of time and space, the meaning of information, the ultimate fate of our cosmos. Yet it does so through processes of extraordinary gentleness. A solar mass black hole will spend more time evaporating than stars will shine, releasing its energy so slowly and softly that the radiation would be nearly undetectable even if you could orbit just outside its event horizon. This gentleness carries a profound message about the nature of change in our universe. The most fundamental transformations, the ones that ultimately determine the fate of all matter and energy, often occur not through dramatic explosions or violent collisions, but through the patient accumulation of infinitesimal changes over cosmic time. Quantum fluctuations near event horizons, occurring trillions of times per second, but each carrying away almost no energy, eventually succeed in dismantling the most massive objects we know. The mathematical harmony underlying this process speaks to something beautiful about the laws of physics themselves. The same equations that describe the quantum vacuum also govern the curvature of spacetime around black holes. The same principles that determine how heat flows through materials also predict the temperature of radiation from evaporating black holes. The universe reveals itself to be deeply unified, with each phenomenon connected to every other through elegant mathematical relationships. Perhaps most remarkably, the physics of black hole evaporation suggests that the universe possesses a kind of memory. That information about every star, every planet, every complex structure that ever existed is somehow preserved in the subtle quantum correlations of Hawking radiation. Even as black holes transform gravitational order into thermal chaos, they maintain perfect records of their own history, written in a quantum language so sophisticated that we're only beginning to learn how to read it. This preservation of information across cosmic time scales means that nothing that ever existed is truly lost. The carbon atoms in your body, forged in the nuclear furnaces of ancient stars, carry with them the quantum signature of those stellar lives. If those stars eventually collapsed into black holes, their stories would be encoded in Hawking radiation that will outlast the deaths of all the stars that will ever shine. The time scales involved in this process stretch our understanding of permanence and change. When we observe a black hole today, we're seeing an object that will continue its patient evaporation long after our sun has exhausted its nuclear fuel, long after the Milky Way has merged with Andromeda, long after the last stars have formed from the diminishing gas between galaxies. Yet even these cosmic monuments to gravitational persistence eventually surrender to the gentle insistence of quantum mechanics. In the far future, when the universe has expanded and cooled to near absolute zero, the soft glow of Hawking radiation from evaporating black holes will provide some of the last sources of energy and warmth in the cosmos. These gentle thermal whispers will carry the accumulated stories of billions of years of cosmic evolution, converting the gravitational fossil record of stellar death into the most basic form of energy: random thermal motion. The final explosions that mark the endpoints of black hole evaporation will be like cosmic fireworks scattered randomly through space and time, each one representing the conclusion of a story that began with the collapse of a massive star billions of years in the past. Between these brief moments of brilliance, the universe will be filled with the patient whisper of evaporating black holes, each one slowly telling its story in the universal language of thermal radiation. As you drift towards sleep tonight, carried by the gentle rhythm of these cosmic processes, remember that you are made of matter that emerged from the hearts of ancient stars. Matter that carries within its quantum structure the memory of stellar birth and death, nuclear fusion, and gravitational collapse. The same physical laws that govern the evaporation of black holes also determine the chemical reactions in your brain, the flow of electrical signals through your nervous system, the peaceful transition from waking consciousness to the quantum mysteries of sleep and dreams. In sleep, your brain performs its own form of information processing, consolidating memories, solving problems, and preparing for the experiences of tomorrow. Like a black hole slowly converting gravitational order into thermal radiation, your sleeping mind transforms the organized experiences of the day into the background patterns of memory and understanding that shape your ongoing journey through consciousness. The universe itself might be understood as a vast sleeping mind, processing the information accumulated over billions of years of cosmic evolution through mechanisms we're only beginning to comprehend. Black holes serve as cosmic dream processors, taking the complex histories of stellar death and galactic evolution and slowly converting them into the simple, universal language of thermal equilibrium. Rest now in the knowledge that you are part of this vast, patient, cosmic process of transformation and preservation. The same quantum fields that create Hawking radiation also enable the neural processes of thought and memory. The same curved spacetime that surrounds black holes also determines the gravitational embrace that holds you gently to the Earth's surface as you sleep. Tomorrow, the universe will be slightly older, slightly more expanded, slightly cooler. Billions of black holes will have emitted a few more photons of Hawking radiation, carrying their ancient stories a tiny bit further into the growing darkness of intergalactic space, and you will wake to participate once more in the magnificent, ongoing experiment of consciousness, in a cosmos that preserves perfect memory, even as it embraces perfect change. Sweet dreams, fellow traveler in this patient, evaporating universe. May your rest be as peaceful as the gentle whisper of thermal radiation from the most distant black holes, and may you wake refreshed and ready to explore more of the beautiful mysteries that surround us in this cosmos of quantum wonder and gravitational poetry. Thank you for joining me on this journey through the gentle science of black hole evaporation. Remember to like and subscribe if you enjoyed drifting through these cosmic mysteries. And until next time, sleep well under the quiet glow of evaporating black holes, slowly returning their borrowed starlight to the infinite darkness from which all light emerges.